Welcome back. In this video, we'll look at the noise cancellation system. And here is a short story. Imagine that you made your favorite soup, you had enjoyed it, and then you went in and washed the bowl. What happens is you leave the bowl on the table, and there is one single drop of water up on the rim. What does this water droplet do? It just doesn't sit there. It'll fall down. So the gravity grabs it and it pulls it down the steepest curve of the porcelain surface until it settles perfectly at the very bottom of the bowl and the absolute lowest point. And this is exactly what we do in machine learning. Except that we don't use gravity, we use an optimization algorithm called the least mean squares LMS or Widrow-Hoff learning. And in our last two videos we built the hardware for our filter on the math hardware, and we proved that the statistical math behind it does work. So today we are going to put them all together and see how it comes how it all brings this to life. So we are going to look at the error bowl, that is the performance surface. We are going to then derive line by line how the ADALINE network dynamically slides down uh, slides down that surface to find this optimal weight down here. And in doing so we will also look at the nice plots of the signals and the noise that are plotted in Python. Let's first draw the noise cancellation system that we are talking about. So I'm going to take some time and draw it. Let's get the pencil and we'll use this noise cancellation system. Imagine there is a person here and the person has these electrodes that are sort of stuck on the scalp, and those are wired to catch the EEG. So these are wired here and those will come in here. So this is the signal S, that is the actual EEG signal or the brain wave that we are getting here, and it has a random behavior based on what the person is thinking. It can change, and then this is the place where we are going to show that this actual good signal gets mixed with something called as noise. And so for the noise we say that there is the machine that is plugged into the wall, and therefore there is some noise of around 60 hertz that is coming in from the on the wiring that's in that building maybe. So that particular, so let me just use this. You have this going this way and there is this noise that goes up here, and there we do one more thing, which is we uh, create a box, and what this box is the noise path filter. And this noise goes up here, and together then what this outputs is a signal which has the original signal, but then it also has a whole bunch of noise in it, and we can write that out. This is what we are going to call M, that this is the contaminating noise. So let's use the same color here. This is M, this is contaminating noise that is coming from this wall, and thus what we get out there is a contaminated signal, and this signal we are going to denote it as T. Again, we come down here and we add this summation or plus sign. What we intend to do here is down below we would have output of ADALINE network, which we call as the adaptive filter. So let's write that adaptive filter. And this adaptive filter, what it will do is it will output a wave that would essentially match the contaminated noise that is in this signal. So it is trying to predict this M value. And what we do with that, what we do is we subtract this value, which is the predicted value A, from that signal T, so that we sort of eliminate this. So T is made up of S and M, and what we do is we try to find A which is sort of same as M and just get rid of M from there, so we are left with a clean signal. And so we can write that out here: adaptively filtered noise to cancel contamination. And what we are left with an error, but unlike the error that we have known previously, this error is something that we would like to have, because that error is nothing but the actual original signal that is inside of the EEG that we measured for the person that we have shown there. Okay, so that is the overall picture or the conceptual idea that we are going to work on. This is the error, and here what we are going to say that the adaptive filter is trying to minimize the error. It's trying to bring the error down, and by doing so it's trying to remove this 16 hertz noise that is there from this original EEG signal. And this entire system that we have is the noise cancellation system, where this part right here, that is where the ADALINE network is working. That's where the LMS algorithm is working. We can now draw this as a neural network diagram, and the way we would do that is as follows. Let's get the colors here. The first thing we do is we we find the VK, which is the noise, and then we bring the noise in, and here is the delay block that we know, we drew that earlier. That's the delay block, and there will be this which will also serve as an input. So in the summation, what we get are two inputs. One is the current value and other is the delayed value. The current value would have a weight of 1 1, and the delayed value in this case will have weight of 1 2. And then the output of this sum would be nk, that would go into the Purlin function, which will output ak. And this part right here, this is the input, this one, and then this part all the way up to the A, that is the ADALINE. And together this entire thing is the adaptive filter that we showed earlier. Again, just to summarize this, what we have here is a person whose brain wave signal is SK. So brain wave signal is SK right here, and that is what we are trying to monitor. But the wall outlet creates a electrical noise and down here, which we say is VK, and that passes through a hidden noise path filter, which is here, and that mutates into contamination M, which contaminates the actual EEG signal. And so what the doctor actually records is the target signal, which is TK, and TK is equal to SK plus MK. So as you see above, it is the mix of the actual signal and the noise. And our adaptive filter, as we have seen here, it takes the input vector Z or Z, which is input vector Z, which is like this part right here, directly from the raw noise source. So we are using this right here as an input. The ADALINE network C does not use the EEG as input. That's a very clear distinction I want to make. It just uses the target, which is a mixture of the signal and the noise, to find the error. Right. So the input is pure signal that we are getting here. Imagine that's the one that's coming from the wall. So what we have here are two weights. We are assuming that we have two weights. There's this one W11 and we have another one W12, and we are assuming there is no bias in this particular exercise we are trying to do. So the ZK that we have, the input vector, consists of VK and the VK minus 1, that's the delayed data. The network then uses, uh, as we saw, it uses the taps, the delay taps, to calculate the output estimate. So we use this delay taps to calculate the output A, and the AK is equal to W11 dotted with VK plus W12 dotted with VK minus 1. And so when we say we are finding an error, we are actually looking at EK, which is nothing but TK minus this AK that we find above. Okay. So the entire math revolves around these equations that we have. Let's formally begin writing all the equations for the adaptive filter. We know that the R, which is our input correlation matrix, is given by the expected value of Z transpose. Then the cross correlation matrix H, that is the correlation between the target and the input, is given by the expected value of H, with the target T with Z. And then Z itself, as we saw, is VK, that's the current data point for noise, and then the previous data point for noise. And if you remember, we are looking at just two inputs, so just one delay tag. Now the target T, as we saw previously, T of K is a mix of the signal Sk and the noise Mk. Now we can use this to get our R. So if we were to uh, do the uh, do the dot product, we would get expected value of V square K, then expected value of Vk, k v k minus 1, and then here we have expected value of v k minus 1 v k followed by expected value of v square k minus 1. Likewise, for h, we can get the general equation, which would be E expected value of S k plus mk, mk, and that's the part for the t right here, and then we have the vk that comes from the z, and the second one would be expected value of S k plus m k, and the difference is going to be, instead of just vk, we have vk minus 1 because we are doing a dot product with the z that we have. Now with this, what we are going to assume is that the input signal that we have is uh, is is given to us, and the input signal is given as input noise, not the signal, input noise is given as vk, that is equal to 1.2 sine 2 pi k by 3. So that is our random signal uniformly distributed between minus 0.2 and plus 0.2, and this is a 60 hertz sine wave, and that is sampled at 180 hertz, and that is a nice equation we have for noise, and we'll work with that. Now in the EEG we also have some noise, and to create that noise we are going to use the same thing except just shift it a little bit by pi by 2. So the mk, we will write it as 0.12 sine 2 pi k by 3 plus pi by 2. So we now have this noise, which is something that goes here like this, and then we have the noise for the signal, so EEG signal noise, so that's something like that, and that would be mixed in with the EEG. So I don't know how the EEG looks, but maybe something like this. So our task then is to find a way to remove this noise from the EEG by training the ADALINE on pure noise, identifying what pure noise looks like. So we can get started with first calculating the value. Given that we know what the V is, what is M is, with using the values we have for V, we can go ahead and calculate the values that go into the input correlation matrix R. And for that, we start out with calculating the expected value. So expected value for V squared is equal to, we are now using this relation that we have, that would be 1.2 squared and into sine 1.2 squared sine, let me put that this way, 1.2 squared sine 2 pi k by 3 square of this. And remember that uh, because this is a wave, we need to sum it over an interval, so 3 cycles, so therefore we have k is equal to 1 to 3, and we are taking the expected value is the average, so we have to divide it by total. So the total here is 3, and so that's our that's something that will get us the expected value. Here we have the sum, and here we are trying to get the average. So this comes out to 1.2 square 0.5, that is equal to 0.72. Likewise, we calculate the value for e, v squared k minus 1, and that would be same as e v square k, which will be equal to 0.72. Now we calculate the expected value of these combined. So e v k dot v k minus 1 is equal to, so this is going to be 1 by 3 sigma k is equal to 1 to 3 1.2 sine 2 pi k by 3 multiplied by again 1.2 sine 2 pi, this time k minus 1 by 3. That's what we have, and if we again go through the process and solve it, you'll get 1.2 squared 0.5 cos 2 pi by 3 is equal to minus 0.36. So these are important values we have. We can now plug these back into our earlier matrix, that general equation that we wrote for matrix R, and so the values that we have is 0.72 on the diagonals, and off diagonal values are minus 0.36. Awesome. So we now have this part done. Let's keep going. Now what we'll do is calculate the values for h, which is, we are done with this part and we're done with this. Now we need to work on this one. So for h, if you remember, we can uh, write it as h is equal to let's see, where is it? Yeah, so we already know that this is what we have. So what we'll do is we'll look at each of these one by one. So we'll look at the top one first, and that is equal to, so let me write it again, expected value of sk plus mk times vk. If we expand this, what we get is expected value of sk times vk plus expected value of mk times vk. Now here, as if you have looked at the previous videos, we specifically talk about how two independent signals cancel out or average out over time to 0, and that's exactly what we are going to use here. What we say is that because this sk, which is the signal, the eeg signal, and vk, which is the noise that's coming from the wall, they are independent, and 0 means, so each of them by themselves tend to go to 0 if we average them out over time. So therefore that term goes to 0. So therefore this term goes to 0. And the second term, which is this one, if we try to expand it, that also goes to 0. So this mk vk is equal to 1 by 3 sigma k is equal to 1 to 3 0.12 sine 2 pi k by 3 plus pi by 2 into 1.2 sine 2 pi k by 3. If you solve this, this also goes to 0, and therefore the first element in our mid vector h, this element, this is just 0. Now let's look at the second element where we are using this k minus 1. So again we write it the same way: expected value of sk plus mk times vk minus 1, that is equal to expected value of sk vk minus 1 plus expected value of mk vk minus 1, and uh, as we said before that the first term, which is this one, was 0 in this case. In this example the first term is as well 0 because this signal and these are independent and they have a 0 mean, so this again goes to 0. Now the second term is not 0 this time, so if we look at just the expected value of mk vk minus 1, that is equal to 1/3 sigma k is equal to 123 0.12 sine 2 pi k by 3 plus pi by 2, and the second part is 1.2 into sine 2 pi k minus 1 by 3. Yep. So that's what we have, and this, if you solve this, it comes out to minus 0.0624. So the h vector that we have, it has value 0 and minus 0.0624. So those are the values we have. Now based on this we can calculate the value for x star. So we can calculate the value for x star, which is going to be x star is equal to the inverse of h dotted with inverse of r dotted with h, and so the value we have for r is 0.72, 0.72 minus 0.36 minus 0.36, take the inverse of that and dot that with the value of h we just found, 0.0624. That gets these values, if you solve them, minus 0.0578 and minus 0.1156. So these are the values for the weights. So these are the values for the weights we have. And weights of yeah, so minimum mean square error solution for the weights. What we do next is we try to go back to the Taylor series and see what we get using that series. So let's go down here and write out the Taylor approximation. We know f of x is equal to c minus 2 x transpose h plus x transpose r x. Uh, we have previously derived this equation, so if you are not sure how we got this, I suggest watching one of the previous videos. Now because we have this, we already know what is x, we know what is r, we know what is h, so all we need to do is just find the c right here. And to find c, uh, we can do the following: we can find the expected value of t squared k, and that is going to be equal to expected value of t is nothing but the target, which is the signal EEG plus the noise mixed with it, that is we denoted as M. So this is going to be SK plus MK, and we square that. So that is what we have. Now what we do is expand this. If we expand this, I'll start from here. We get, let's write it out, sk square plus 2 sk mk plus mk squared, and I forgot the expected, so we have to write it. So the way we would write this is expected value of s square k plus 2 can be outside the brackets, expected value of sk mk, and then we have plus expected value of m square k. So we would write it like that instead of writing like this. Now in this case, again this term a goes to 0 because the signal is independent of the noise. They both average out to 0 over time, because if you remember, the signal stays half of the time it stays above 0, half of the time it stays below 0. So positive negatives, they are over time they cancel out and come pretty close to 0 when we take the average. And that's the expected value because the denominator becomes large. Now what we are left with is calculating the ESK and the EMK. Now to calculate this very first one, what we do is we do the following. We calculate E s square k as by using integration. So we use 1 by, and the reason, so here is what we do. We know that the signal is uniformly distributed between minus 0.2 and plus 0.2. So the probability density function is 1 divided by 0.2 minus minus 0.2, and that is 1 divided by 0.4, and that's what we are going to use. And to get the um, complete, to compute the mean square value, we are going to use integration. So here is how we would write that. We would use 0 minus 0.2 to plus 0.2 s squared 1 divided by 0.4 ds, that is equal to 1 divided by 0.4 s cube divided by 3. This goes from minus 0.2 to plus 0.2, and that gets us 1 divided by 1 divided by 1.2, because 3 times 4 times 3 is 12, 1.2, and then we have 0.2 cube minus 0.2 cube, and if we solve this we get 1 divided by 1.2, and this is 0.008 minus minus plus 0.008, and that final value we get is 0.01333. So that is the value for our expected value for s square k. That's the signal. Likewise, we calculate the expected value for the m, the expected value for the m square, and this is going to be, let's delete that. So this is going to be equal to, so the mean square value, so what we are trying to calculate, this is the mean square value, and same thing, this is going to be the mean square value. This is equal to 1 by 3 sigma, and 1 by 3 sigma k is equal to 1 to 3 0.12 sine 2 pi k by 3 plus 1 pi by 2 square of that, and that comes out to 0.0144 divided by 3. K is equal to 123 cos squared 2 pi k by 3. 2 pi k by 3, and we can then keep going further down this, and so this is 0.0144 divided by 3 cos squared 2 pi by 3 plus cos squared 4 pi by 3 plus cos squared 6 pi by 3, and this will get us 0.0144 divided by 3 minus 0.5 squared plus minus 0.5 squared plus 1 squared, that is 0.0144 divided by 3, and this is 0.25. So this is let's write it out, 0.25 plus 0.25 plus 1, so that comes out to 1.5, and if you do the multiplications you get 0.0072. That is the value for the m square k. Alright, so we now have the values for these two, so all we need to do now is add them up as we see here, and so not there, sorry, as we see here. So the value for final value for C is going to be equal to 0.01333 plus 0.0072, and therefore the C is equal to 0.0205. So we have that. Now we have the R, C, H, X, we have everything. So we can now put everything in the final equation that we have. So where is our Taylor series? Right, this one. So we can put everything now in this equation right here. And so what we have is f of x star is equal to C. So C, we know what it is. It is 0.0205. That's the value we have for C. And the next one is x transpose H. And so if we try to look at the values, there we have, this is minus, so let's change this. We have minus 2, so minus 2, and then we have x transpose values are minus 0.0578, minus 0.0578, minus 0.1156, minus 0.1156, and the value for R, value for H we just found out, which was, where did it go, this one, 0 and minus 0.624. So this is 0 and minus 0.624. 0. Let's see, where is this? 0.0624. That's what I was thinking. This is 0.0624, and plus we need the terms for x transpose Rx. So transpose would be this 0.0578 minus 0.1156. That's the x transpose part. The R is right here, 0.72 on the diagonal, so 0.72, 0.72 minus 0.36 minus 0.36, then we have x, which is 0.0578, and this is minus 0.1156. All right, and so we start solving this. We get, this is going to be let's see, so this is going to be minus, so this would be 0, the first term will be 0, then 0 plus, this is minus 0.1156 times minus 0.0624, that gets us plus, this is 0.0072134. Right, so we have that, and then for this term minus 0.0624, and then again we have minus 0.0578 minus 0.1156. All right, so this is, so this part right here comes down to 0 plus minus 0.0624 times minus 0.1156. That gives again 0.0072134. Awesome. So those are the same numbers we are getting here. So in the end, what we have is 0.0205 minus, again we have 2 times this, so essentially they'll cancel out. So what we get is 0.0205 minus 2 times 0.0072134 plus 0.0072134. That gets us the magic number, which is 0. So let's erase this. We get 0.01328,652. So that is the value we have for f of x. And why is this number magical? And the reason is because this number, we said that this is the minimum, so this is the minimum mean square error. So this is the minimum mean square error. Essentially what we are saying that this is the error. So if you remember the diagram, that what we said was the output, whatever was there, was E, which was the error, and this error was nothing but the actual signal that would be left out after we subtract the noise from it that we get from the ADALINE, right? So we subtract the noise, and so all we are left with the error, which is the signal. Now how do we know this is correct? Because if you try and match this number, with the number that we already we have seen above, let's keep going, and you see this number. This number is 0.0133, and we are also 0.013, so 33 if you round it off. So awesome. So that is the big reveal in this case, where we can see that we used the delay blocks to store little bit of data points in the history, and then use the ADALINE network to train on that, to train on the noise. ADALINE does not see the EEG signal. It just trains on the noise, identifies the noise, and that's what we removed from the actual signal. That's how we clean the signal in a way. Now let's look at this Python implementation of the algorithm that we just talked about. Here we initialize the weights to 0, -2. We chose the learning rate as 0.1, and here we are simply doing the same calculations that we did manually just now. We have the k -1. We have the z vector. Likewise, we have the s and m, which is based on this sign, and then we what we have is the uh, t target, which is the mix of s and k. Note that here we are using random uniform for the actual the signal. We calculate the output A, we calculate the error, which is the difference of the two. We update the W by the same approximate steepest descent that we talked about. We just add 2 times alpha plus error, 2 times alpha into the product of error with the input Z. And whatever W we get, we are storing it in a history, and then that's what we are plotting down. So this is just a fancy way to plot this contour that we have, but the main core calculation of the code is right here in these lines. All right, so here is the plot, wonderful plot. We can see that we start around here. That's our initial guess. 0 was the W. X axis is W1, Y axis is W2. We have two weights, two inputs, easy to see on a two-dimensional plot. And that W that we guessed initially, these were the weights. As you can see, we were far away uh, from the minimum, and as we move, you see this is going random directions, but we are going downhill. Note that if you travel along any of these lines, you are at the same height. If you move across the lines, it means either you are going up or down. Given that this is the minima is down here, so when we travel towards it, we are actually going down. So we are stepping down, and we are going in zigzag way, and finally eventually we reach the bottom of the plot. We have minus 0.09, minus 0.1, and here what we calculated was minus 0.05, minus 0.1. Not identical, but they are pretty close, and I'm guessing if we maybe if we continue with more iterations, maybe we get that number. um, so we could try that. Now let's say if we try 1,000 times and then run this, we get even smaller values of it. So that that is what we have. If we just do maybe 50 iterations, we still get there. Now we have numbers that are a bit higher than what we found. So I think this would change based on what values we use, and maybe one of the reason is we are already at this lowest point, and it is jumping around as you see. And here the optimal that we get is, if you see on the top corner in the legend, we do have the x star, which is minus 0.0578 and minus 1, and that's what we got here. So that is the optimal value that we find by calculation. Now let's look at what this weight adjustment means for our signals in the time domain. All right. So here is the next plot I wanted to share, which is this one. In the top graph, the black line is our raw signal. That is recorded raw recorded signal TK. It is a giant rhythmic 60 hertz sine wave that completely obscures everything. And if a doctor looked at this, they would say nothing but electrical interference. But watch the blue line, which represents our network error, EK, and that is the restored signal that we have. So for first 0.05 seconds, the blue line looks chaotic as the weights undergo rapid changes. If you look at the contours, so they change drastically, and that's why this is uh, jumping around initially in the initial learning phase. But by the time we hit 0.2 seconds right here, that's when the weights have found the bottom of the bowl, and the filter is then tracking the wall outlet noise perfectly and subtracting it. After this, the giant sine wave, it disappears from the error stream, and what is left behind is a clean, beautiful, isolated, high frequency random waveform. And that's we are saying that that's the patient's actual brainwave signal that has been completely rescued from the noise, as we see down here. So in summary, what we have looked at in past these 3-4 videos is that we expanded and proved that every single algebraic step of quadratic performance equation, we looked at that, that it will converge. We calculated the weights W1, W2. We also verified that the minimum possible mean square was 0.0133. As we saw, it matches with the signal S square K. So now you understand the architecture, the statistics, and the real-time optimization loop of this adaptive noise cancellation. In the next video, what I'm going to do is try to apply this adaptive filter with ADALINE on a real world recorded voice and show you what works, and I'll also show you what does not work and what are the limitations of this particular network. Awesome. So I hope you enjoyed these particular series of videos from past 3-4 videos to really do a deep dive and understand how the ADALINE network works. Thank you, and I hope to see you all in the next project video. Bye for now.